So welcome to the lecture series on analysis of structure. This is part 3 of the rolling loads and influence line diagram. Today we are going to see using influence line diagram how to calculate absolute shear force and absolute bending moment for various loads. So the absolute maximum shear force in a beam is defined as for a given load system when it moves from one end to the other. Depending upon the position of the load, there will be maximum shear force at every section. For load position, there will be maximum shear force at every section. This maximum shear force is called as absolute maximum shear force. I will try to understand this by using an example of a simply supported beam of span 12 meters, and we are considering a section at suppose 8 meters from the left support. So this distance is 8 and total length is 12. So this ordinate will be minus 8 by 12 and the remaining length is 4 and the total length is 12. So this ordinate will be 4 by 12 on the positive side. So the load position for absolute maximum positive shear force, we are concerned about absolute maximum positive shear force. So we should ignore this part and we should try to focus on this only, or how the ordinate changes when the position of section is changed. So next section we are tracking towards the support A, and what we find is that this value which was earlier 4 by 12, now it is 7 by 12. That means when section is towards the support A or left support, the value of maximum positive shear force will increase. The positive ordinate is increasing. Suppose further we move up to this point. So this ordinate will increase like this. Now this will be, so this is going to be 10 by 12. So there is no rocket science in this. For maximum positive shear force, the section should be at the support itself. Then only we'll get the maximum ordinate as 12 by 12 or 1. So this is what we conclude. Absolute maximum positive shear force in a beam is nothing but positive RA only. Now we consider negative shear force. So 8 meters from the left support. So this distance is 8. This is minus 8 by 12. We go back towards the support A. What we see that ordinate is decreased. So to get the maximum negative value, we should move towards the support B. The absolute maximum negative shear force will occur at support B, and we can conclude that absolute maximum negative shear force in a beam is nothing but RB minus RB. So two things we have done. Absolute maximum positive shear force will be at RA and absolute maximum negative shear force in a beam will be at RB. Absolute maximum shear force in a beam for positive shear force, it is nothing but ILD for RA, and this is absolute maximum negative shear force. This is ILD for minus RB. So we know that if the shear force, if a vertical force is on the left side of the section, we take it as positive, because right down, left up, this convention we are using as positive. So RA is a, from left side it is a upward force, so we should consider it as positive shear force, and RB, which is referred to as negative shear force. From this sign convention also, if section is here, the load is moving from right up, is considered to be as negative. So in short, we can say that in a simply supported beam, for any kind of load, maximum negative shear force will occur at right hand support. We'll solve a problem. We are given a system of load. So 5 loads are there, and suppose this 10 kilonewton load is leading. So loads are 10, 20, 15, 10 and 20, and the distance between the loads is also given, and it is crossing a simply supported beam of span 10 meters. So this is a simply supported beam of span 10 meter. We assume that load is traveling like this and this 10 kilonewton load is leading. So we have to calculate absolute maximum positive shear force and absolute maximum negative shear force. So we know that for absolute maximum positive shear force, we should draw ILD for RA. So this is our ILD for RA. The ordinate at A point will be 1. Place all the loads such that the loads are towards the support A only. We can multiply the load with the ordinate. So for this 20 kilonewton load, which we are considering as W1, so Y1 will be 1. This is suppose W2, so we'll measure distance from this support. So this distance is 8, total length is 10, so this ordinate is going to be 8 by 10. Now for this load, we have to find this ordinate. So what is this distance? From 8, from this distance from this load to the next load is 1.5, so we'll minus 1.5 from this, so this will be 6.5. So ordinate will be 6.5 by total length 10. Now the next load is at 1 meter further right, so from 6.5 we should subtract 1, so we'll get 5.5. So for this last load, the section is here, so we want this distance. So what is this distance? It is 5.5 minus 2, so we'll get 3.5. What will be this ordinate? It will be 3.5 by total length 10. So this is Y1, this is Y2, this is Y3 and Y4 and Y5. Simply we will substitute and we'll get the absolute maximum positive shear force in a beam for the given load. So when we put the value, we will get this answer. Now we'll solve for absolute maximum negative shear force. So absolute maximum negative shear force is nothing but you should draw ILD for minus RB. So this is already I have drawn ILD for minus RB. Ordinate at B is 1, so we have written it as 10 by 10. Place all the loads such that this load, head of the load is at the section. So 10 into 1, what is this distance? This is 2 meter. This is 10 by 10, so this is going to be minus 2, that will be 8 by 10. So 20 into, next load is 1 meter on the left hand side, so this will be, instead of 8 by 10, it will be 7 by 10, and this one will be, further you deduct 1.5, so it will be 5.5, further you deduct 2 meters, so it will be 3.5. So simply multiply W1 Y1, W2 Y2, W3 Y3, W3 W4 Y4 and W5 Y5, and you put it, you will get a value of 49 kilonewton. So this is trial 1, in which we see we have put the rightmost load on the section, rightmost load on the support itself. Now we'll try another possibility, so that this second load, that is 20 kilonewton load, is at the support or at the section. So let's see. So now in this case 20 kilonewton load is at the section, ordinate is 1, that is 10 by 10. The subsequent load is 1 meter behind it, so the ordinate will be 9 by 10. Subsequently the load is at 1.5 meters, so 9 minus 1.5, that is 7.5, and this is minus 2, so 5.5 by 10. So we'll multiply this, so W1 into Y1, W2 into Y2, W3 into Y3, W4 into Y4, and Y5 is gone, it is outside the span, so no need to consider this. So when we put this value, we find that we got a higher value. So whenever we are given a series of load, we should do some trial error method to calculate the value of absolute maximum value by placing all the loads towards the right support, or for positive shear force we'll place all the loads towards the left of the support. And what we found that since this 10 kilonewton load was a small load and subsequent loads were heavier than this, so there was a possibility that heavier loads are multiplied with higher ordinates, it will give critical shear force. So same thing happened when we placed our 20 kilonewton load at the support, we got the maximum negative shear force. So this should be B, because we are trying to find the absolute maximum negative shear force, so it will be at support B. So now we'll try to find what is absolute maximum bending moment. See, for the system of load, there will be one position because of which there will be maximum bending moment at every section. So for that load position we will get the maximum of maximum bending moment. So that value will called as absolute maximum bending moment. And this value, absolute maximum bending moment in simply supported beam, usually occur near the midspan only. So we consider a simply supported beam and our loads are ready. So these many loads W1, W2, W3 and W4 are passing across it. So we'll identify the critical load. One of these loads, W1, W2, W3 and W4, one of these load is going to be a critical load which is so placed in the beam such that midspan C is equidistant from the resultant of forces and critical load WCR. So first thing what we have to do is we have to identify the critical load, then we have to calculate the reaction and the position of the resultant and place the load in such a way that C, which is the midspan of midpoint of the beam, is equidistant from critical load and position of the resultant of the load system. And next thing is the absolute maximum bending moment will occur under the critical load. So what we need to do, we need to understand how to calculate the resultant of the force system, and the next thing is how to identify the critical load. So it is very simple. Suppose these are the 5 loads and we will name them W1, W2, W3, W4 and W5, and we want to calculate the resultant. So what is the resultant? So we know from the mechanics that resultant R square is equal to sigma fx plus sigma fy square. So we know that since there is no horizontal load, so sigma fx term is going to be 0. So we can say that R square is nothing but equal to sigma fy. We can rewrite as resultant, value of resultant is nothing but summation of all the vertical forces. So we will add up all the loads. So 20 plus 10 plus 15 plus 20 plus 10, it will give you the value of resultant, 75 kilonewton. So this is the resultant of the force. Now next thing what we want is find the position of the resultant. So let x is the position of resultant from the first load. So suppose this is my first load, we will name it as x. So we want to find the position of the resultant x. For that what we do, we use the Varignon theorem. So f1 x1 plus f2 x2 plus f3 x3 plus f4 x4 plus f5 x5 divided by summation of all the forces. So this is nothing but sigma fy only. So this is the first force and we will try to find the value of the distance. So x1 is going to be 0 because f1 and it is coinciding, so no distance from it. Second force is 10 kilonewton, so it is suppose at a distance x2, so the value is 2 meters. The third force is 15 kilonewton, the distance is x3, so from here to here it is 2 plus 1.5, that is 3.5. Fourth floor is 20 kilonewton, so the distance is 2 plus 1.5 plus 1, that is 4.5, and this distance is the sum of 2 plus 1.5 plus 1 plus 2, it is equal to 6.5. So we will put all these values x1, x2, x3 in this, and eventually we will get the value of x. So what is x? It is the position of the resultant from the left support, or from the first support. So this is the final diagram. We wanted to find two things to calculate the value of resultant. So we have calculated the value of resultant as 75, and the position of resultant also we have identified, it is 3.03 from the left support. Now we can identify which is the critical load. So there are two forces to the left and right of the resultant force. So the force which is nearer or heavier to the resultant force will be considered as the critical force. We will crown this one. I will say that this is the critical force. If we measure this distance, it is 3.5 and this distance is 3. So we can say that 15 kilonewton load is more nearer to the resultant force. So this is the critical load. Now you want to find the critical load position for absolute maximum bending moment. Identified the critical load. Now what we have to do, we have to place the midpoint of the beam C such that it is equidistant from R and critical load. So this is our critical load, and the center of the beam, should be so placed that it is equidistant from the resultant and this critical load. So from here to here the distance is, from left support to this critical load, the length is 3.5. so this distance, the distance between resultant and the critical load is 0.47. We will assume it like this. We have to place this midspan of the beam such that they are equidistant from critical load WCR and resultant. So half of the, from this setup we understood that from the center of the load, the critical load is at a distance 0.235 meters towards the right. So this is the center of the beam. Since the beam is 10 meter long, we have marked the center point. Now this critical load should be at a distance 0.235 meters from the center of the support. So we'll place it. So the first force is going to, what we are going to place is the critical load. Then we know that the second force is 1 meter away from this force. So we can't change this distance between the forces. We can only place the critical load. Rest of the loads will be placed as per their original distance. So this is the load on right hand side of the screen. Now what about the left hand side? This load is 1.5 meters from the critical load, and further it is 2 meters from this 10 kilonewton load. So we have placed our loads as per the requirement for absolute maximum bending moment. Let us try to find the length. So this point is this midpoint. So these two distance are 5 meters. We'll split it, and this distance is 0.235. So absolute maximum bending moment will occur under this critical load only. So what is that distance? It is the distance of section from left support is going to be 5 plus 0.235. So this length from left support to this is 5.235, and from it will be 5 minus 235. So 5 minus 0.235. So now let us draw the ILD for bending moment at section under the critical load. So we'll get the absolute maximum bending moment will occur under the critical load. So this is our section. On left hand side the distance is 5.325, and on the right side the distance is 4.765. So this is the ILD. What will be the central ordinate? It will be the product of these two, 5.235 into 4.765 divided by 10. So this is our central ordinate. It is equal to 2.5. Now the other loads, the ordinates under the other loads we have to calculate. Suppose this is W1, so we'll name it as Y1, this is Y2, W3, Y3, and W4 and Y4. Right, so we'll calculate this Y1. So what we do, by similar triangle will, so general equation will be 2.5 divided by 5.235 into x. So this distance is going to be x. So for y1, 5. So this distance is from here to here, it is 3.5. So we can write 2.5 into this value is the value of x. Now we want to calculate y2. So y2. So what is this distance? What will be this distance? This distance is going to be total length 5.325 minus this length is 1.5. So it will be 5.325 minus 1.5. So calculating this, we will get the value of y1 and y2. Let's move to the other side where this equation will change because lengths are changing. So we'll substitute the values in this equation to calculate y3. So 2.5 by 4.765 into x. So this distance is going to be x. 4.765 minus 1 divided by 4.765 equal to 1.5. 0.97. Similarly for y4, we'll substitute the value as 4 point. So because this distance is 3, so this distance is 3, so it will be 4.765 minus 3 divided by 4.765 equal to 0.93. So all the ordinates are calculated, 5 loads are there, all the 5 loads and ordinates are known to us. Now to calculate the absolute maximum bending moment in the beam for the given load, simply multiply W1 into Y1 plus W2 into Y2 plus W3 into Y3. So there are 5 loads, so there will be Y5 into Y. So when we multiply all these, substitute all these values and solve this, we will get the absolute maximum bending moment as 120 kilonewton meter.